chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all have encountered with purely deterministic and prescriptive approaches and methods. We've been calling these approaches and methods RIPB for short. The Nuclear Energy Innovation and Modernization Act specifically mentions RIPB. If you look around, you will find it hard to find any place other than ANS, outside of NRC, of course, that has as much information and guidance on RIPB. Overall, there is a lot of guidance available on RIPB, but most people have not had reason to become familiar with the information. This is primarily because the conventional approaches still dominate most things we do, including standards development. RP3C has been having these community of practice events regarding RIPB and associated methods such as systems engineering to enable practitioners to share their knowledge and experience. We've been scheduling these sessions on the last Friday of each month. Today, we will hear from the vice chair of my committee, Rob Hayes, who's a professor at North Carolina State. He's going to be talking about as ALARA, as low as reasonably achievable. I requested Rob to make this presentation because lately ALARA has been in the news because of the way the staff has tried to incorporate some of these ideas into Part 53. So anyway, Rob is very familiar with this, and I appreciate that he agreed to make this presentation. Rob, please go ahead.
Okay. So can you hear me good?
Yep.
All right. So I actually served as a ALARA coordinator in the DOE complex for a number of years. Before I was an academic, that's where I was. A lot of it at WIP. I was the person the scientist over the emergency response and the recovery. And I did the consequence assessment for that as the ALARA coordinator at the WIP site. So then I came to academia, and now I teach health physics and pretty much everything associated with that. And so now I'm going to talk about how, in my perspective, that risk-informed performance basis applies to ALARA as both an academic and as an individual who served a number of years doing ALARA in the DOE complex, not in the NRC world. So to start off with, you really need to focus on risk management in order to be able to have that first part of RIPB. Here is one way to define that. If you take the traditional risk is equal to consequences times probability, you need to assign a metric to that. How do you define the consequences and the probability? Some kind of a numerical standard that you're going to have. Once you've done that, then you can apply a numerical value to risk. In my opinion, one of the biggest problems that we've had in the nuclear industry is that the public conflates zero risk with safe, so that unless you have zero risk, you're not safe. You can only be safe if risk is zero. That contradicts ALARA, and it contradicts common sense. But then again, a lot of things could be said about that, because literally nothing has zero risk. Even doing nothing has some risk. So there's always a non-zero risk. And so if you try to attain that with money, you're going to spend a lot of money to get that risk starting to approximate a zero risk level. So here is another way to come up with that. This is going to be consistent, I'll show you later, with the DOE concept on ALARA. You need to ascribe some kind of a numerical monetary value. So for example, if you have some outcome A, and that's got some risk associated with it, then which is given by B, then you come up with how much it would cost to reduce A in terms of risk per dollars. Once you've got that, then you can just plug and chug over into this formula over here. And for some fixed amount of money, let's say you got $10 million to reduce risk, then if that $10 million then is F, then this formula then tells you how much you need to spend on each event D. It's F times D gives you that fraction of money that you should spend on each. That way you're not spending an enormous amount of money to reduce a small amount of risk. You're trying to spend a little bit of money to reduce a lot of risk. And that's kind of the approach that you're trying to do, but it's being weighted. And that's all that the formula does, is it just gives you a way to weight it. And what we'll see from ALARA is that this is consistent with my understanding of ALARA from the DOE complex, which is entirely consistent with my understanding of ALARA in the NRC world. So from the guidance for 10 CFR 835, which is the DOE regulation for radiation protection, it actually calls it out. You need some dollars per rem. Now, when we were at the WIP, the guidance that you got was around $2,000 per rem, which was what they had, which was what some of the guidance we got from other DOE sites. We realized that if you burn out an individual by exceeding their ALARA goal, the ALARA program would say, well, then you cycle them out, and then you got to train somebody, so that all costs combined meant that it was about $12,000 per rem. That way, if you didn't burn out a person, you didn't have to replace them, and it's very expensive to replace, say, for example, a radiological control technician. It's not cheap to get a new one in to do that and take them away from other jobs. So the point is that you have this numerical criteria that you can apply back to that formula that I used before, or you can come up with your own metric or your own approach. But this is what the guidance actually states. These are just quotes from the guidance document. So it becomes legitimate to ask, how much is a millirem worth? If you've got a millirem, how much is that? Should I be spending? Once you've got that number, you can do that result. That, however, does beg the question: if somebody's got a legal exposure, then if it's legal, how much effort do you need to reduce it? Think of the speed limit, right? Is that even an appropriate analogy? Maybe, maybe not. It can go either way. But the point is that if you take ALARA to extreme, then if it's already legal, saying, you can't go 1 mile an hour over the speed limit or something like that. Maybe that's a good analogy, maybe it's not. However, I would tenet that anybody who's been properly educated, and this is again just an opinion as a former ALARA coordinator and as an academic, it should be recognizable, readily recognizable, that $1 million to avoid a millirem is just gross negligence. There are far better ways to spend, hundreds of millions of dollars than trying to get doses down to fractions of a millirem. That's just, in my opinion, that's obscene, simply because of things like this. Natural potassium is essential to life. You will die without it. In fact, our high sodium diet has led some physicians to prescribe this, potassium chloride, as a dietary supplement. And the literature is clear. If you don't get enough potassium, you can have all kinds of health effects. A healthy amount of potassium will give you some dose, because potassium 40, naturally occurring in potassium, that's the ingredient here in no salt. It's got a high energy gamma and a high energy beta that's stronger than both the beta from cesium and the gamma from cesium. And so it scales with muscle content, so that if you're a large muscular male, you can get 40 millirem per year. If you're a small petite female, you can get 10 millirem per year, just from internal potassium, just what's essential to life. And so if you're going to spend millions of dollars to reduce dose down below these levels, that begs some real serious questions. That would be my opinion. At these levels, at these dose levels, it just starts to become ridiculous. Let me put it into a different perspective. 10 millirem. Right now, 10 millirem is the dose, 10 millirem per year. That's literally the dose for an EPA license. When I was at WIP, that was our license limit. 10 millirem per year to the nearest resident was the maximum that could be in the effluent, unrestricted to the environment. And this is where regulations live, way down here, up to 100 millirem, which would be an NRC limit. Now, I'm going to point out that all of these are all orders of magnitude on this DOE dose range. From 1, 2, and 3, these are all orders of magnitude going up here. And these lower 3 orders of magnitude, there are no measurable medical effects associated with these. So that if we go up an order of magnitude from where the regulations are to where we do medical diagnostics, At these dose levels, again, there's still no measurable medical effects. And yet you can get backgrounds substantially above these levels. But this is the kind of thing that you might get, say, a REM from certain medical exposures. By the time we go up another order of magnitude, all the way up to the 1 to 10 REM level, still no measurable medical effects. This is where you start talking about linear no threshold. Does the linear response at higher doses at an order of magnitude above this, do those cancer probabilities linearly extrapolate down through this level here of 1 to 10 REM? Again, this is many orders of magnitude above the 10 millirem at the EPA limit or the NRC limits. And so with no measurable medical effects, this is still not safety related as with all of these others. These ranges right here are what I'm going to argue are where ALARA applies. It's not safety related. It's related to your ability to control radioactive materials and prove it with a regulatory compliant ALARA program. And so with that, you get an order of magnitude higher, and now you get measurable effects. By the time you're above 10 REM, 10 REM is the lowest that any of the journal papers have even suggested for measurable medical effects. And that's only for children and not for adults. Adults, it goes up to around 20 or higher. And some things that are of interest is that even in this low dose range, this is where evacuation is recommended by the EPA. At 1 REM, that's the minimum that they'll start to recommend it. And at 5 REM, they'll recommend that's the maximum that they would allow somebody to not do an evacuation, even though there are no measurable medical effects in these ranges. Now, once you get above the cancer epidemiology, that where we know it's linear, then you start getting up into where you get to the LD50s in the hundreds of REM. And that's where people literally start dying. These are the Hiroshima survivors and so forth, where we got to see these. And then at the very higher, where you're talking about thousands of REM, that's where you're literally killing tissue with radiology. And so you can see from these various orders of magnitude that these levels 1, 2, and 3, this is not safety. 4 and above, that is safety. So I can characterize it with this chart, right, with this table right here. Starting again in the similar orders of magnitude, you start talking about background. You start talking about, this is at the millirem, that's where you start talking about daily average dose from background to an individual. 10 millirem, again, this is an annual background from internal dose, or it's the EPA limit to the public. By the time you're at 100 millirem, now you're talking about X-ray levels, say to the pelvis or hip, and the public limit for the DOE and the NRC. At 1 rem, you could get this again from medical exposures, say for a CT scan of your hip or torso, but it's the protective action guideline from the EPA for evacuation. Similarly with 5 rem, that's the maximum they would go for evacuation. And even if the linear no threshold did apply down to the 5 rem level, it's still only about 0.2% increase in cancer, which admittedly you would want to reduce if you could. What we do find from the literature is that in these levels, everything else becomes dominant in terms of what's going to give rise to cancer. Stress, health, those kinds of things dominate any kind of cancer predictive capability. In these levels, it's just not measurable. There's too much noise. But by the time you're at 10 rem or above, there you start to be safety related. This is where your unresolved safety questions will kick in if something's going to apply. But at doses down here, we're strictly talking ALARA. So what is ALARA? I really haven't said anything other than it's not safety. I would tenet that the best analogy to communicate ALARA is QA for control of radioactive materials or ionizing radiation fields. So we not normally think of it as time, distance, and shielding, but how do we implement that? In the same way we do with quality. You define your goals, you measure them, you analyze them, you improve them, and then you control them. And you do this cycle. It's the same thing we do with quality. However, when you're talking about ionizing radiation, and the analogy that I would prefer to use to describe how it works is if you think about the Carnot efficiency for your steam cycle in a nuclear reactor. Now, you do want to get as close to that Carnot efficiency as possible, but when you start getting really, really close, it starts to get really, really expensive to get a little bit of improvement. And so you're going to need to optimize it. That optimization is this ALARA process right here, where you say, and you go back to that risk definition. How much does it cost to reduce the dose? If it's a little bit of money to get a lot of reduction, that makes sense. If it's a lot of money to get a little bit of reduction, that doesn't make sense. And so it's the analogy that I would use to describe ALARA in RIPB is as a quality program with an efficiency goal in mind, where you're trying to get as close to that efficiency value as possible, and you're just under continual improvement, just like quality. So that's how I would communicate it. If you think about all of the radioactive material programs that we have in our nuclear facilities, there's a bunch of them. But typically what we do is we fold that all into ALARA. But it's really just comparable, if not an equivalency to QA. Am I getting what I expect? Once I've defined my goals, I say, this is the kind of dose that I think that I can achieve with a highly disciplined operation and procedures and so forth. And then I want to go under continual improvement. And so that's why I've highlighted here, your radiation protection program's QA is ALARA. It's not safety, it's just QA. A regulatory compliant ALARA program, in my opinion, I would tend it, in my professional opinion, is quintessential proof that you can safely control radioactive materials and ionizing radiation fields. If you have a compliant ALARA program, that's it. That's by definition, I would argue, that you are able to control nuclear materials and ionizing radiation fields. So let's start talking about when we get back to these levels of natural background. An analogy that I like to use to communicate this dose rate effectiveness factor is in terms of work, energy deposition or energy conservation. If I jump from a 10 centimeter block 100 times, I would believe that any certified trainer would say, that's a good idea, that's healthy, that's aerobic, do that every day. However, in terms of the work or the energy deposition, that's equivalent to jumping once from a 10-meter block, which could be lethal. It would certainly hurt me. It would break a bone, almost certainly, if not something far worse, I don't know. But the work is equivalent. One is protracted, one is acute. The body is designed. It likes the 10 centimeter jumps, lots and lots of them, right? Jumping up and down, lots of aerobics there. But the 10-meter block, although it's equivalent, it's still extremely outside of my design specification for this biological mechanism here. Now we know that there's something very similar in terms of dose rate. So that when you look at that linear model above 10 rem, we know that if you protract that, it does not have the same effect. So that if it's spread out over a year, it's at least a factor of 2 less harmful. And so you can say, well, that's just a dose rate effectiveness factor, or you could go to a linear quadratic model. And the ICRP has come out on this and saying, yeah, 2 is a nice conservative value. Some papers have said it could be more than an order of magnitude above that, but it's at least 2 based on the consensus for a conservative model. So I mentioned that I was at WIP. I was working there when they had the event, and I did the emergency response, the recovery. I did the consequence assessment for that. And I just want to make a little analogy here with Yucca Mountain, in the sense that Yucca Mountain's already cost well over 10 billion. WIP has cost about half that. It's about halfway done. And maybe that's a good analogy, maybe that's not, but I would argue that one of them is pretty successful and the other one is just a hole in the ground. But there's some caveats here. So one way of looking at this, so I mentioned at the beginning, you've got to ascribe some kind of a metric. Here's one way of coming up with a metric. I'm not going to say it's good or bad, but it's an interesting way of looking at it. If the 2 million curies that have already been disposed of at WIP were considered in terms of, if you removed it all and took all of the radioactivity and put it into pills and fed it to people, and you assume that 10,000 ALI, which is kind of in the range of the dose that Russian spy got, Litvinenko, when he died from the polonium exposure, somewhere in that range. So you make that assumption that that's your LD50, then you look at and you say, well, it might double by the time it's done. And if it doubles by the time it's done, it's going to be about $10 billion. Well, even at $10 billion, if I look at how many LD50s I'm removing from the biosphere permanently, it's only about $100 per LD50 permanently removed from the biosphere. Now, maybe that's fair, maybe that's not. Maybe it's fair to compare WIP with Yucca Mountain, maybe it's not. But it's an interesting way of looking at it. Now, WIP had a stellar record. They were just doing phenomenal in terms of their performance, the activity there. This is a photograph of the underground with some of the transuranic waste. This is one of the miners, the teeth there, it's mining out the salt. And they were just doing phenomenal. They had an amazing record. They were actually called the crown jewel of the DOE complex. They had triple crown, ISO 14001, safety star, all of the metrics that you could come up with to look at safety. And then Los Alamos sent this drum that deflagrated and aerosolized about 7 curies of americium with nitric salts. Now, like Fukushima, it was a regulatory compliant facility with all the safety systems working. And as a result of this deflagration, this occurred. You can see the doses here that would have been present if an individual had been anywhere in there. This had been validated. This is the consequence assessment that was done for that release. Why this is significant is that this terrified people, and yet the americium, it was really just all americium. The americium that was deposited was comparable to the amount of americium that was there before they built the WIP site just due to global fallout. It's just because it had a regulatory compliant radiological air monitoring system that we were able to get the precise measurements of the air that was released in this consequence assessment. So that quite literally, if you look at the Smith Ranch, the nearest resident, or you look at the right on the outside of the fence, this would have been a regulatory compliant release if it had been controlled and it had been planned, because the dose to the nearest member of the public would have only been 3 milliram, which is below the 10 rem threshold, and the 25 milliram threshold to get up to the 100 milliram limit. So it's well below the 100 milliram limit for the fence, and it was about a percent of the limit out there, just under a percent of the limit for the Smith Ranch. So it would have been compliant with the EPA license and with the DOE regulations if it had been planned and if it had been controlled. But because it was neither planned nor controlled, it was nightmare, right? Literally, they had a dirty bomb go off in the repository, but nobody was hurt outside of fear. People panicked, they were terrified, it was horrible. As a result, they've had to have some additional ventilation, they've had to build these new facilities, they have a whole bunch of new equipment. Because of the contamination in the underground, there were these red areas, or areas where the roof started to cave in because they didn't have access, right? They had to have full contamination controls to get down there. Whereas before, it was a start clean, stay clean. And so they didn't have the infrastructure to suddenly do contamination controls in a high contamination environment in a salt mine. That was something that took some time to get up to speed so that they can do the ground control, basically putting in the bolts and so forth to keep the salt still so that it doesn't fall down. And as a result, now they're in full contamination environment or full contamination controls as they're doing the waste and placement in the underground. However, along comes this very strange and unexpected result, the Oversight group. So in order for New Mexico to agree to have WIP, they wanted academics who were not paid by the DOE directly to do oversight, so that you had technical expertise overlooking the scientists and engineers at the WIP to double check them. And this is at the Carlsbad Environmental Monitoring and Research Center. And one of the scientists there came up with this paper, which is interesting because this paper said, technically your license allows you to do 10 milliram per year. All that infrastructure that I showed you was going to cost about $500 million, plus it put them back about 2 or 3 years. And you still had to pay all the infrastructure to keep the complex up and running, which was about $250 million per year. On normal times, it actually went up to just under $350 million per year during the recovery. And so that money was still being spent, but there were no cans being put in the hole. And what this paper showed was that you could run unfiltered and still be in compliance with your license and the DOE regulations. And I was in the process of doing the work to actually assay the exhaust shaft at the time. But the point being is kind of what I was saying before, right? If you're regulatory compliant and then you're trying to go back to zero, because that's what all that equipment did. It was trying to go back to zero releases instead of meeting the 10 milliram per year limit at about $500 million. So because of this, people were saying, why are we spending $500 million to go back to zero release when we still can be compliant with our license right now? So that's a pretty important question. Are you really willing to spend $500 million instead of putting that to some social program or whatever else you think might be appropriate to get back to zero release when you can do it in a way that is compliant, and then you just apply ALARA to that. That's what I would argue is the right way to go. So that still hasn't been completely resolved. It's a very valid question. So given all that, I would argue this analogy between ALARA and QA, in that QA, I think we can all agree, is not a safety issue, but you can't have safety without it. You're never going to get safety significant or any of those systems meeting the requirements without a quality program. But quality applies to a lot of other things besides safety significant. It even applies to balance of plant. It applies to all of those things. So it's necessary, but not sufficient. ALARA is kind of similar. You're not going to have a good safety program if you're not controlling your radioactive materials. I don't know how you're going to do that. I mean, that would be pretty surprising to see somebody to do that, but ALARA is controlling your radioactive materials. It's making sure that you're doing it compliant. It's making sure that you're not getting leaks, you're not getting contamination. If you are, you're tracking it, you're trending it, you're seeing if it's an issue, you're seeing if it's okay, if things are getting out of hand, if things are under control. If things are under control, that's what ALARA does. So from that perspective, I would say that, in my opinion, you cannot say that anybody has been harmed if you violate only ALARA. If all that you violate is ALARA, you've got problems. You've got some big problems. You've got loss of control. You've got loss of those features that are ensuring that you've got adequate time, distance, and shielding for the materials that you have. And so with that, I did this in a half hour as requested, and I am ready to take questions.
Thank you, Rob.
Yeah, thanks, Rob. I guess we haven't seen any questions in the chat yet, but maybe at this point, because there aren't that many people, you can unmute and pose a question to Rob if you wish.
I'd like to make a comment. This is Steve McDuffie with Department of Energy.
Hello, Steve.
You're right about the new ventilation system at WIP. It would be unnecessary for reducing doses for what's in the mine now, but the ventilation system is being relied on in case that kind of accident happens again, because it happened once. We can't guarantee it'll never happen again. So that's why the main reason the department is investing all that to put in that ventilation system, not just to make the people feel good about nothing more coming out of the mine. And in fact, we are looking at doing some unfiltered ventilation in the next couple of years before that system comes online.
Good to know. Thank you.
This is Brian Grimes. I have a lot of history on ALARA, and it causes me to question the concept itself. In 1971, the concept was brought over from European agencies, and my advice was that we'd be better off with requiring margin below 100 millirem and doing lessons learned on encroachments on the margin, which is a more performance-based approach than trying to analyze a lot of detail, and would leave the systems or the processes of the licensees to show themselves by performance instead of compliance with processes. So my view is that there's really no benefit of keeping exposures in the plant extremely low, and that if you did a proper PRA risk assessment, you would certainly conclude that there's no benefit for spending money. Right now we have a 2 millirem de minimis level, I believe, but even above that, well above that, there's no measurable financial or health benefits to the ALARA program.
So I would follow on that with an observation, if one were to take that approach, and that's that right now, the ALARA programs that are out there don't have, as a general rule, a direct correlation between contamination levels and dose. The contamination levels of control are more based on detection and discrimination from background, as opposed to the dose limits. So if you wanted to take that approach, you would need to come up with these conversions for contamination to dose. And largely why that is typically not done is because the amount of variability that's there, right? How do I say, if I've got contamination in the hood that I don't want, because I don't want to spread contamination, how do I correlate that to dose? I'm gonna have to make a lot of really gross assumptions, and probably some extremely conservative assumptions that could be entirely variable, so that the uncertainties that are associated with that would be quite large. So that I think probably you already recognize that when we do contamination control in nuclear facilities, it's largely based just on that, controlling the radioactive material and making sure that nothing's leaking, using these levels that are comparable to what we can readily discriminate from radon progeny deposition on surfaces.
But it seems to me a performance-based approach would be to carefully monitor exposures. And if the exposures as a result of the contamination are not detectable, then you don't have a problem.
So I don't disagree with you, but I would point out that if you've got a leaky source, you're probably going to want to seal that and control that, right, before it gets worse. And so, in my opinion, the benefit of the ALARA program is to make sure that you're looking for it, so that you're not being careless about leaky sources, or you're not careless about large pencil beams or any other kinds of radiation dose potential, that you're continually monitoring it. So that's why I come back to a QA program. You can tailor your QA program to your specific operations, because I actually, me personally, I like the ALARA program. I thought it was good and healthy if it was done right. And when it's done right, in my opinion, is when it's done like a QA program. It's to inform the decision makers about if and when they need to give anything some attention. Does this require attention? Does this require additional stuff? Or is the regular continual improvement that we're doing, say through lessons learned and through, closeout job briefings and so forth, and incorporating that into the RWPs and the ALARA reports and the ALARA goals appropriately. If it's done right, I think it's healthy, as insofar as a QA program is healthy for any nuclear facility. Again, that's just my opinion.
Rob, in a way, I think I can draw an analogy with two things. One is the reactor oversight program, that the NRC has for operating facilities, has something they call green findings. These are essentially minor findings that constitute some kind of a citable finding, but those things generally just go into some kind of a corrective action program. And as long as there is due diligence taken to show that when something is found, you do something about it and don't ignore it. That's one way that I think one could look at this. The other question in my mind is, do you see a parallel with the precautionary principle? Now, that again is something that we imported from Europe. And, to me, the precautionary principle is problematic. And to some extent, these tendencies to go towards zero risk is sort of a manifestation of the precautionary principle. Do you have any comment to offer on that observation?
Only that when I've interfaced with members of the public on concepts of radiation safety, the anti-nuclear people have the perspective that nuclear is not acceptable unless it has zero risk. And if we allow ourselves to continue to try to spend more money to reduce the risk down to these levels, then we're just going to cost ourselves out of existence. It just becomes ridiculously expensive to try to do that. And now that's up to the the bean counters and the decision makers to what extent they want to do that. But in my opinion, when it comes to ALARA, that's just QA. You need, in my opinion, you need a QA program for radioactive materials. I call that ALARA. And then you need a safety program that deals with these large doses, right? So that's where the safety basis comes from. And ALARA supports the safety basis, just like QA supports the safety basis. But ALARA should never, like I had said in the very back here, one of my conclusions, if you're already compliant, then there's a big problem, a potential big problem if you're trying to substantially reduce those, because at that point, it just needs to be in terms of demonstrating control, like the green finding, like you put out. That's how I would see it. Now, another person could do it something differently, and I'm not sufficiently familiar in detail with where this came from in Europe. I'm only familiar with the DOE complex in terms of ALARA, and more specifically ALARA at WIP, because I was the ALARA coordinator there for a long time. Did that help?
Yeah, thanks. Since we do have a little bit of time, I just want to make the connection between ALARA and the Part 53 ongoing rulemaking. The thing that I saw is, to some extent, because of the way the risk management in the ALARA program could work with dollars per person rem, the staff in Part 53, I think, was using it as a proxy for cost benefit analysis. And, I think that is problematic, is to think of ALARA as implementation of a cost benefit approach. But, there are some common concepts involved, but, a cost beneficial safety enhancement to a reactor design has really nothing to do with the kind of thing in ALARA. So anyway, there's a question from Bob Martin. Do you see it?
Yeah. Hi. I'm Bob Martin. I'm from BWXT. I'm sitting in for Steve Schultem, who I guess attends these on occasion. But anyway, I wanted to stimulate conversation. I'm involved with some advanced reactor design, and do have a task in 2021 to look at occupational dose, radiation protection issues, and specifically at analysis, coming up with analysis methods that could aid in, say, just operational maintenance activities for a small reactor design. Anyway, just to stimulate conversation, I threw out this question here, asking about if there's any gaps in existing ALARA analysis methods, which I presume have been largely based on, operating experience, that might make them insufficient for design of ALARA programs for advanced reactors.
So thank you for that question, Bob. I would say the answer is yes. And it comes when you don't do something like this. You don't have a quantitative metric for cost effectiveness. Then it can become easy to think, oh, well, my regulatory limit is 10 millirem per year for my EPA license. So, if I can reduce that by 50%, that must be worth a lot of money, right? We're talking 5 millirem, right? How much money is 5 millirem worth? That could be, really painful if you're going to spend. And so if you're not using an RIP, risk-based, and you don't have a quantitative, if you're just saying, well, it's ALARA and we can reduce it by a bunch, if you don't have some risk so that you can compare one risk against and the cost for that, then you can make some big gross errors based on not having quantitative comparisons to make. That would be my answer to that.
So what do you do? I mean, there is obviously no data for new reactors because they don't exist.
So I would argue that it comes down to going back to the technical basis, that you just need to be able to make sure you have a way of monitoring any kind of releases, any kind of airborne contamination, dose rates, that you have ways of monitoring all those things that we have in our in a compliant ALARA program. And that would be part of your safety analysis. That would be part of your radiation protection program. So once you've done that, demonstrated that you can properly monitor all of those things, that would be an indicator, a preliminary indicator that you're losing control, then you're good, right? It just comes down to due diligence. Can you prove that you have due diligence in terms of controlling radioactive materials?
Are you doing the best you can? Yeah, no, I appreciate that. I totally see that. All right, thanks.
Okay, I think, we have run out of questions. Rob, I want to thank you for making this presentation. And, as Pat said, this event has been recorded, and, the slides and the recording will be available on the ANS website under RP3C. And, you will also see the events from the past. We've been doing this over the past year, and this is the second one for 2021. I'd like to suggest that if you have, if you'd like to offer to make a presentation to share your experience with risk-informed and performance-based approaches, I would very much welcome your volunteering to make a presentation. With that, again, thanks all for participating. Pat, is that it?